Thanks a lot, Manuel, for this very nice, very kind introduction.
Thank you.
And thanks for this very nice invitation. I'm very happy to be part of this One World seminar. Thanks to Juan, thanks to all of you, Monica, and everybody. And today maybe I'm going to do a kind of survey on the diffusive Hamilton-Jacobi equation on various qualitative properties, some recent developments, also some more classical facts. So maybe it will be rather like a review of results, maybe a few ideas, no full proofs probably because it would be too much. So maybe I will give some ideas here and there, but more like a survey if it's okay for you. So so the equation on the first slide. So it's very simple looking, deceptively simple in fact. So the source, it's a heat equation with a source term, which is the norm of the gradient of u to the power p. It's a diffusive version of the Hamilton-Jacobi equation. We will see some motivation in a few moments. And usually we studied for in case of in the bounded domain with homogeneous directly boundary conditions. So I would like to change slide, but it's a little stuck. So I don't know. Is it Zoom? Okay, Zoom is up. Okay, oh, it's fine. Okay, so let me start with some basic motivation from stochastic control theory. So you just consider a control stochastic dynamical system, which means you have a stochastic process labeled by x sub s, and the variation of the process is given by a control term, which is alpha s, and a Brownian term. So xs stands for the position of a particle. The control means that here the operator can choose the velocity of the particle up to, of course, the noise. And the initial data, which I mentioned in the previous slide, will correspond in the stochastic problem to a space distribution of rewards in the following sense. If you give yourself a time horizon, let's say s equal t, so the final reward will be u0 computed at x sub t, provided x stays in the domain until time t, and 0 otherwise. And of course, so this is the reward, but there is a cost, obviously, and the cost is just a power of the control, and the power is the conjugate power of the p of the exponent p of the equation. Of course, as long as xs stays in omega. So the net gain is the difference between the reward and the cost, and it is the this minus the integral between 0 and the first exit time, or if it does not exist, integral of alpha sub s to the power p prime. And so there is a very nice theorem from essentially due to Barl and his co-authors, which says the following: the value function of the game, which means the optimal gain is given by the unique viscosity solution of the Hamilton-Jacobi equation. The diffusive Hamilton-Jacobi equation. So there is a unique, in fact, the theorem says that there is a unique continuous viscosity solution, and this solution coincides with the highest possible expectation of the gain, conditioned by the initial position of the particle, which is at time 0. You start from point x. Okay, so this is the connection, a very precise and very strong connection between the game and the equation. So sometimes it gives some intuition, and sometimes in the other way, you have some properties of the game which you can derive by studying the PDE. It works in both directions, but since I'm not an expert in stochastic problems, to me the idea is rather to say something about the behavior of the PDE, and maybe in some cases we have some interesting interpretation in terms of the game. Okay, that's it. Of course, okay, again, my my slide is a little stuck. I don't know why. Is it something common with Zoom that okay, now it goes. Okay, there is another motivation where I will go briefly on that because it's well known and maybe the connection is not so physical, but it gives some hint. There is a famous KPZ model for surface growth. U is the height of a surface growing by ballistic deposition of dust like alumine. And now the gradient term is a growth term, and diffusion is related to the relaxation of the interface by surface tension. And in the stochastic version of this, you have a noise, again, a different kind of noise, not the noise like in the stochastic control game, but a game in a noise in the PDE. But you also have the deterministic version, which is well studied in the physical literature. But physically, it's not so clear if P bigger than 2 is really meaningful. And mathematically, P greater than 2 is the most interesting case, which for the game means that the cost is subquadratic between 1 and 2. P prime, it will be between 1 and 2, and P is greater than 2, which is our case of interest. And of course, it's also a model case in the qualitative theory of nonlinear parametric equations, and it can be seen as a counterpart of the very well studied Fujita, so-called Fujita equation, and there are many experts in this audience and this seminar. So I will try to draw some parallel between properties of the two problems. So now basic properties, this is completely standard because we are not interested in irregular initial data. This is also an interesting question, which has been studied quite a lot, but this is not the topic of this talk. So I will always assume that I start from some nice initial data, which also means for the stochastic game that the distribution of rewards is a smooth function in the domain. So C10 initial data, you have a unique local maximal classical solution, and it may blow up in finite time, but we have also a viscosity solution, as we already mentioned in the theorem of Barl, and we will see later that there are some very interesting things about continuation of classical solution as a viscosity solution. So this will be mentioned later. But our first order of business is to understand what happens with the classical solution. So there is a very easy maximum principal estimate for U itself, just by maximum principle. This is completely clear. But keep in mind that the local existence space is C1. So of course, it's not enough to control U to extend the solution. You also need to control the gradient. So it means that in case you have a blow-up alternative, if the solution is not global, this means that the gradient of solution will escape in finite time, while U will stay bounded. And as you know, this kind of phenomenon is now well known to be under the name of gradient blow-up. So this is our main topic today. Okay, so there is a clear dividing line in terms of P between up to quadratic and more than quadratic. It's a very classical dichotomy. Of course, everybody, as most people know, from the 50s and the classical work of the Russian school, when you have L infinity estimate and the growth in the gradient is not more than quadratic, then you have automatically C1 estimate. Like, for instance, Bernstein type arguments, and you have over techniques, which means that for us, since most people in this audience maybe are interested in the singularities, we have, of course, top expert in singularities here. If we want to explain singularities, we need to go to the super quadratic case. Otherwise, nothing really exciting will come out. Okay, so it's well known that you have, for this problem, we have both large blow-up solution, large initial data blow-up solution, and small initial data global decaying solutions as a typical situation in the superlinear parabolically problems. And so there are various criteria for blow-up, sufficient conditions for gradient blow, which are known. For instance, if this initial data isn't sufficiently large in some sense. There are various ways to measure this, but even some LQ largeness is enough. Then you will have T finite, which means that U itself will not blow up, but the gradient of U will blow up. Okay, and various kind of proofs, energy or eigenfunction arguments. I will not spend time on this. And of course, you also have small data global solutions by some more or less standard super solution arguments. And this is not the kinds of solutions I really want to spend time on in this talk. Okay, so this is a basic situation. Now, there are also many other topics for this equation. You can be interested in the Cauchy problem. So the Cauchy problem, there are no singularities at all, even when P is very big. It doesn't change the nature of the problem because, as we will see, the singularities for this problem are essentially a boundary phenomenon. So since there are no boundaries, nothing weird can happen. So there are many detailed studies of symptotic behavior for Cauchy problem, but it's neither our topic. And many other questions like extinction for sublinear case, P-Laplace diffusion, rough initial data, boundary trace, initial trace, controllability, many very interesting things. And I will not touch this today, but these are worthwhile also. Okay, so now I would like to concentrate on the question about singularities, both in the classical solution framework and in the viscosity solution framework, which means that there is the first time where the solution leaves the space C1 because the gradient becomes unbounded somewhere. And so this is the GBU gradient blow-up singularities. And we would like to understand the typical question about in the qualitative analysis of evolution PDEs, which are the time rate, the singular set, and the various notions of profile, space-time, similar, refined. As you know, there are many notions of profiles in various problems, and it's usually an exciting topic. And then, as usual, one can ask, what happens after death? Is there life after death? And what does it look like? And we already know that there is a continuation in some rather weak viscosity sense. And it's not completely intuitive how this continuation happens. Although, of course, most of us know the definition of viscosity solution, but there are some delicate issues about in what sense the boundary conditions should be understood in the viscosity sense. And in fact, this is really where the subtleties arise. The solutions are zero, but not in the classical sense, only in the viscosity sense. And we will go back on this later. So the first, and we will study such questions as continuation, loss of boundary conditions, but also then recovery of boundary conditions and regularization, which means that the solution will become usually a classical solution for all large times, but in between there will be some very peculiar phenomena of oscillations, like multiple gradient blow-ups, multiple losses, and multiple recoveries of boundary conditions. So this is an exciting variety of behaviors, and so I will try to explain some of these things. And of course, sometimes try to make comparisons with the Fujita equation, but the comparison sometimes are limited because the equations have quite different structures and properties. Okay, so let's start with the time rate. This is the first order of business usually. And as you know, the lower estimate and the upper estimate can be of quite different nature. So the lower estimate, we have, let's say, a fundamental like a fundamental speed, which is a minimal speed. So the minimal speed for the problem is this one. The gradient in soup norm cannot blow up slower. Okay, some people call it faster, but let's keep things simple. So let me say cannot be less singular than this exponent 1 over p minus 2. Okay, so it's a key number, and it's not so. It makes sense because, as we know, p equal 2 is a critical exponent for existence of blow-up. So p minus 2 is something consistent in a sense. So under this form, it's very general. It's for any domain and any solution. No additional assumption. Under this form, we proved it in the rather recent joint paper with Alessio Porretta. But there were partial results, either in one space dimensions or for some particular classes of. Okay, but under this generalities, under this precise form, it's this paper. So maybe let's give a very quick sketch of proof. So the idea is to work with u sub t. So u sub t, of course, satisfies the linearized equation, which is a Fokker-Planck equation with drift, and the drift is something which is quite important in this drift in the problem. Maximum principle will tell you that u sub t is bounded. Okay, but although it is bounded, that's one of the difficulties of the problem. Many quantities are bounded, but still the singularity is encoded in some of their derivatives, or some in some way it is encoded, although the many quantities are bounded. So it's not so easy to extract information on singularities from some quantity which is bounded. So you have to work more. So the idea is to try to see what is the evolution of the gradient of u sub t. That is the idea. So since you have a nice equation for u sub t, you can use some typical devices like variation of constant formula, semi-group estimates, and these kind of things to derive a differential inequality on the maximum in space-time past cylinder for sup of gradu. So call it M, and M will satisfy almost everywhere an inequality like M prime less than CMP minus 1, because in some sense it is a linear equation with a drift which grows like M to the power P minus 1. So this is kind of linear estimate, which gives you this. And then when you integrate this, it will give you a lower bound. As you know, the signs become reversed after integration up to the final time, and will give you a lower bound, not for gradu infinity, but for the supremum of the gradient over the whole past cylinder. And then you have to work more to forget about the memory, forget about the past, just have retained the piece of information concerning the time t and not the other times. So, and this requires some more work, which is not so obvious. But basically, here's how the proof goes. Okay, but maybe more important is the remark that this rate, so 1 over p minus 2, is not self-similar. So this is a very important fact. It's a kind of equation where self-similarity is violated, even for low values of p. As you know, in the Fujita equation, self-similarity is violated for high dimensions or very particular values of p's, and there are many deep works of, for instance, Manuel and his group about this. But in our case, the violation is systematic. It is never self-similar, whatever the value of p and whatever the solution. And the reason is just that if you compute you do just a basic dimensional analysis of the problem. So you compute what should be the exponent for backward, let's say Loret type backwards of single solution, and the exponent should be k divided by 2, where k is this number. And when you compare, so what is so maybe there's a little mistake. No, okay, now okay, this is for you. Now if you differentiate, you look at the gradient, and so what the gradient, if it were self-similar, it should be with the exponent 1 over 2 times p minus 1. But this number is smaller than 1 over p minus 2. And we know that the singularity is at least of the order 1 over p minus 2. So the singularity is always stronger than a self-similar singularity. So no self-similar behavior for the blow-up here. Not in this, not in the time direction at least. In some, we will see more profiles later, but in time direction, which is normally the very basic estimate, immediately you have violation of self-similarity. So it's quite, it's a bit surprising at first. So now we would like to, of course, to have upper estimates. And as you know, it's a much more complicated story usually, because you have this minimal rate, but sometimes you have faster rates. So for that question, I would like to slightly generalize the equation by adding some just inhomogeneous term. The reason is that I would like to study time increasing solutions, and usually these helps make it's not so clear if you have time increasing solutions without at least time increasing the whole domain. This does not exist for the purely homogeneous term problem, but with inhomogeneities you can get it. So consider time increasing solutions, which means that you start from a sub-solution of the elliptic equation. Then you have the full the rate is from below and from above like before. So it's really exactly 1 or p minus 2, but as far up to now, we need some additional assumptions. It's not completely understood. So in 1D, it's okay. In radial 1D, it's okay also. But if you want to look at more general domains, up to now, we only we don't know what happens when p is bigger than 3. So we can completely understand the problem between 2 and 3, but after 3, it's not understood what happens unless except for 1D. And here I'm talking only about time increasing solutions. So we will see more rates for non-monotone solutions later, but even for usually this is the most stable class time increasing solution. For the Fujita equation, for instance, this is where all the minimal rates are happen. So even for that problem, even for this rather stable class of solutions, we have this strange limitation p equal to. And when you look at older paper of Lasserie and Lyons, for instance, on the elliptic problem related to, again, stochastic control and the so-called state constraint problem, and these things from also mean field games, and this was a basic theory, the basic stage of mean field game theories. So for many estimates, they were also, and still now, I think, they were stuck with p equal 3. For the elliptic, some of the elliptic estimates in the famous work of Lasserie and Lyons stopped at p equal 3 for some reason, and I think even now it's still open. So it seems that there are some serious troubles up after the cubic. Very strange. Nobody knows if it's technical or not. It's quite strange. So of course we'd like to understand this, but we are stuck for the moment. Okay. Anyway, that's let me give some brief idea of the proof. So it's for time increasing solutions, as often case. It's a story about tricky auxiliary functions. So the tricky auxiliary functions, this one was devised by Zhongsheng Guo and Bei Hu in the 90s for the 1D case. So you see, it's a this strange thing, u sub t minus some perturbation of z, which is, okay, this strange, so this is just a perturbation, but this is the main thing, it's kind of renormalized space derivative. So it's really tricky. You plug this into the equation, and you have a maximum principle. J will satisfy maximum principle, so J will have a sign, and when you integrate, you get the desired estimate. So it's kind of much more sophisticated Friedman-MacLeod technique, and maybe even trickier in higher dimensions. What we did with Amala Tushi is to consider this kind of functions. So it's a little different because we have to play with the okay. I anticipate a little bit. We know that singularities are only near the boundary or on the boundary. So the game is often some related to the distance to the boundary. So here delta is a distance function to the boundary. So we have to combine some powers of the distance to the boundary and some powers of u, and subtract it to u sub t, and again look for a maximum principle. Sometimes the completions are quite long. For instance, we did that also for the P Laplace version, the quasi-linear version of the Hamilton-Jacobi with P Laplace diffusion, and we can do this kind of things. Well, this kind of not that precise question, but this kind of auxiliary function, and the proof become extremely technical, but still it seems to be flexible enough. Okay, then in 1D you also need some zero number argument on u sub t for some of the results which I mentioned before. I cannot go to details. Now let's go now to non-monotone solutions. So I don't want to assume time increasing anymore. And as you know, like in the Fujita equation, this changes the behavior a lot. So this is a recent paper with Noriko Mizoguchi. We were able to completely classify the rates for the 1D problem. Of course, it's only 1D because we are pretty much dependent on zero number, and even not just zero number, but also bright group theory. Okay, so the result is like this. There is a classification of the rates are all multiples of 1 or p minus 2. So L equal 1 was the minimal rate, which we discussed before, and actually it is the fundamental, like the first eigenvalue in the spectrum. And then you have the whole spectrum. It's really a spectrum because, as you can guess, there is a kind of eigenvalue problem which is hidden.
Sorry, what is zero element B?
Excuse me?
In point A, with zero is in B. What is B?
Oh, okay, I'm sorry. B is the blow-up set, the singular set.
Oh,
okay,
thank you.
So it means that of course, we are just say on half line or a bounded interval. So and as I said, I anticipate a little bit. Singularities are either at 0 or R or both. There are no other possibilities. So assume, for instance, that there is singularity at 0 at the final time, at capital T, okay? And then, essentially the gradient blow-up rate is maximized at the boundary. So essentially you have to understand how U sub x behaves in time at the origin, at x equals 0. And so it behaves like this. For some, always exists some L such that. And conversely, for any given integer L, at least 1, there exists some initial data such that solution behaves like this. Okay, so it's a complete classification. And so, as added as a remark before, in fact, the maximum is reached. In that case, it's reached at that point, at the boundary point, at least the maximum on the left part of the interval. Okay, this is a statement. Okay, now we have more information because beside the rate, we also have some profile, some classification of the profiles. So it's a kind of bubbling. It's a little bit primitive because it's only 1D. So it's not the same kind of bubbles as in the Fujita equation, for instance, for Sobolev critical case, but it can be seen as a bubbling phenomenon because if you look at the 1D steady states, so you just look at the ODE u prime prime plus u prime to the p equals 0 with u equals 0 at 0. And so it's very easy to compute the solutions. There is a foliation of solutions. In fact, there is a one parameter family of solution obtained by shifting the space variable in a given reference profile, which is a bubble, which we call here the bubble. So the bubble is the singular solution, which is on the black line on top of all the others. This is actually it's V, but actually it's capital U here. Okay, so capital U is the most singular, the maximal solution in some sense, and it is connected to the zero steady state by this continuum, one parameter continuum of steady state, which are very easy to compute. And now in a small boundary layer whose size can be estimated, the solution will behave like a rescaling of the bubble. So a little bit like what happens in the Fujita equation, plus some higher order term, which here it's x squared. So it's valid in some neighborhood, which actually the boundary layer has this size. It's u sub x, the maximum of u sub x to the power of 1 minus p. So of course it goes to 0 as t goes to capital T. And for some special solution, we have more precise asymptotic expansions, but this is for any solution, this is completely general.
What is UA of X? How it depends on A?
Yeah, actually, you see, you have this foliation here. So all the steady states are those guys. Is it visible when I underline in color?
Yes.
Yes. Okay. So this blue guy is the one. You see, one of the is V. Sorry, V. It's V on my picture, but it's U actually. Okay.
Okay.
These are these guys. So it's a foliation which connects 0 to the singular solution, and so of course when A goes to 0, you go to the singular steady state because U0 is U actually.
Mhm.
Okay, so the most singular because then the parameter. So okay, I'm sorry again. This y is a. I'm so sorry. Y is not y. It's a. It's a.
Mhm.
Okay. It's a. Okay. It's v of a plus x minus v of a. So I'm so sorry for the clumsy notation. It's okay. So it's in translation. So they are all zero at the origin. But the only important one is this one, and the others are just obtained by shifting this one. So okay, so it's like in the bubble, like in the standard bubble for the Fujita equation. Okay, now we can also characterize the number L. It's actually given by the number of vanishing intersections of U with the singular steady state as t goes to capital T, which means that, okay, we have zero number theory. It works well for this equation. Even for viscosity solution, it works. But here we are only, for the moment, with only classical solutions. Okay, so as you know, the difference between two solutions, the number of zeros is a decreasing or a non-increasing function of time. Okay, so these intersections there are only finitely many, and the number does not increase. So it has a limit as t goes to capital T. And among these, so after, this means that for t close to capital T, this number is constant because it's a discrete Lyapunov function. So it has to be constant in some neighborhood of the final time. And so let's say there are Q zeros, okay? Among these Q zeros, some of them will collapse to the boundary, and some of them will stay far away from the boundary. Actually, one can rule out oscillating zeros. This cannot happen. It's not obvious, but it's possible to show that the zero either has to go to the boundary or to stay at a positive distance from the boundary, near the blow-up time. Okay, so let's say the number of the zeros of the intersections between U and capital U, which goes to the boundary, we call this number L. And L is precisely the index of the profile. This L here, okay, so this power of here, this is exactly the number of vanishing zeros. So for instance, in the monotone case that we had before, it means that there is exactly one zero which collapses to the boundary at the low time. Okay, and finally we have also complete classification of stability of blow times and rates and profiles. So first of all, the blow time is continuous with respect to initial data if and only if the index L is odd. For instance, L equal 1, which is the minimal case, like in time-reducing solutions. If it's odd, otherwise, if it's not odd, there is discontinuity of the block time. And then once you know that it's odd, you can ask, okay, of course, if T itself is not continuous, it has no meaning to ask about the stability of the profile because everything will go anywhere. But when L is odd, you can ask, okay, for which L do you have a rate and profile which is stable? Which means starting close to an initial data which has index L for the blob rate and profile. Is this preserved for when you start close? Okay, and the reason and the answer is if and only if L equal 1. So only the fundamental profile is stable. All the others are unstable. Of course, it is presumably they are finite codimensional stable. This is a more delicate issue, as you know, many people now in your group, maybe also in Frank Mer's group, and other people are studying this kind of delicate issues. What is the dimension of the unstable manifold of an unstable blow profile, for instance? So it might be that it might be stable up to some finite codimension manifold. Might be expected, but how to prove that? No idea. But for the moment, but if you just ask about rough stability, then the picture is like this. And this for any 1D solution, we have no additional assumptions. Okay, are your proofs difficult to? It's a very long proof, but the first thing to do is to construct special solutions with precise behavior. So it's in the Herrero-Velasquez style, let's say. all type 2 solutions, because as we said before, they are not they all violate self-similarity. So it has to be type 2. And so, of course, now we have a lot of experience with type 2 solutions, starting with the pioneering work of Hero Velasquez and then Merle and his co-authors and your group, and many people now have various techniques to construct type 2 solutions. And so the first thing, at least we followed the approach of Hero Velasquez, basically adapted to our framework because it was enough for our purpose, and it was kind of easier maybe for our problem. So the first thing is to do like Gigacon, to go to similarity variables, and then to do some kind of match asymptotic. So you have an inner region, an outer region, and then you try to do some matching. You can do it formally. This is like physicists do. And if you want to prove the existence, then you have to do it very carefully with a priori estimates, and to do a fixed point argument by a topological fixed point theorem. So of course, there are many experts about this in this audience. And usually the inner region has a kind of quasi-stationary behavior. So basically you just move along the bubbles, you rescale the bubbles. So this foliation of solutions, which I mentioned in the previous slide. And in the outer region, you linearize around the singular steady state. And you can compute the eigenvalues of the linear operator. So you have eigenfunctions, and then you match. And if you really want to do rigorous matching and not just like physicists, you have to do a priori estimate, starting with isolating regions and so on. And it's immediately a 30 or 40 page proof. And then you end up with topological degree. So in a sense, it's now a kind of still difficult, but more or less well-known root map, if we can say like this. And okay, so that's what we do for this equation now in 1D. So this was part B. Part B, let me mention to you, part B is just the existence of special solutions for each L in the classification. Now, if you want to show that any solution has to behave like this, you have to work more, but you have to use part B. You have to use the special solutions. And the idea now is to, for part A, you have to use zero number and break group techniques to compare not 2 solutions, but 3 solutions. So this was done before by Matano and also by Mizoguchi for the Fujita equation for some ranges of parameters. And we could modify, so it's a non-trivial modification because our problem has lots of differences. So we now, what solutions that we compare are, okay, U is a given solution, bring up at capital T. V is a special solution with L vanishing intersections. I mean, the same number of vanishing intersections than U. So you assume U has L vanishing intersections. Take the V, which has also L vanishing intersections. And the third solution is capital U, which is a singular steady state. Okay. And then we do the break group representation of the parabolic flow as pioneered by Grice and van der Vorst in the 2000s, especially for linear problems, and then developed by Matano and others later for semi-linear problems. So we have adapted this to the current problem. So the idea, if you have 3 curves which do not meet at the endpoints, you can lift them as 3D curves by introducing V sub x direction, which means that if a solution, if 2 solutions cross, you have to assume that the crossings are transversal. So this is true up to a finite number of exceptional times, and you can get around this. So at those times where the crossings are transversal, when you say, okay, if it's transversal like this, it means that one has a higher derivative. So it will be in front of the other when you lift to 3D. That's the idea. So this picture becomes this 3D picture here. Okay. And then when you have lifted to a 3D picture, you can interpret this as a braid of 3 strands. Okay. And so for instance, so this is the braid corresponding to this or to this, the same. And as you know, you have 2 generators, X and Y, which are the fundamental crossings like this of 2 strands. And then by just finite combinations, you can represent any braid like this. And so then it's difficult to say more, but the idea is to compare. And the idea is that if U and V have the same number of vanishing intersections, you see that the zeros cannot be lost before capital T. So which means that the number of crossings, the only thing that can happen is that zeros disappear, but this can happen only finitely many times. So you can trace the crossings, and crossing mean losing an intersection means that you lose x squared or y squared up to topological equivalence. Okay, and then since U and V have the same number of vanishing intersections with capital U, only the crossings between U and V can change, but the crossings between U and capital U or V and capital U keep the same number. So this is rigid enough so that you can compute the possible evolution of braids, and at the end you can compare essentially the slopes at the origin, and this means that you compare the braids. So this is a very rough sketch of proof, but it doesn't tell you anything about the technology or how you compute, how you follow the evolution of braid and so on. It's too technical, but this is the basic idea. Okay, now probably I will be short of time if I say everything, so I will pass more briefly on the other things. So blow-up set, as I said before, is a subset of the boundary. So this is now any dimension. This is an older result with Zhang 15 years ago, and this is based on the Bernstein estimate because grad U satisfies this Bernstein bound, whereas the exponent is 1 or p minus 1 in terms of distance to the boundary. Okay, there are more things in that direction, but just remember this this bound. This is the main thing. And this one is self-similar, unlike the other. This 1 or p minus 1 follows the scaling of the problem, unlike 1 or p minus 2. Okay, now okay. I don't go to details about Bernstein argument. So then the question is, what more can you say on the blow-up set once you know it is part of the boundary? Of course, in the radial case, radially symmetric, it has to be the whole boundary. This is clear, but it's not so exciting. So now the next thing we did with Yuxiang Li about 10 years ago was to say, okay, you can localize the singularities in any neighborhood of a point by preparing the initial data suitably. So this is not so surprising. You have to have concentrated enough initial data. So this we could do. And maybe the most interesting things in this direction is single point blow up on the boundary. So single point about the boundary, it's not just concentrating near a point, but concentrate to a single point. So for that, we needed some geometric assumption on the domain, for instance, convexity in the x direction. So this is 2D, just for simplicity. 2D with a flat part near the origin. So the origin is a boundary point. And so we can construct initial data for which the singularity, the grain blow-up singularity, is only at the origin. So which means that the picture on the right is the plot of the final profile as a function of x and y at time capital T. So it means that you have a vertical slope here, but the slope is still high, but of course it's less and less steep when you move away from the origin. So this is the kind of shape of the solution if we have a single point gradient blow-up. Okay, this has been extended in various directions. For instance, Carlos Esteve, who's now a former PhD student, who is now a postdoc in Cambridge, was able to do it for non-flat symmetric domains because we had a lot of difficulties. At the time we were not able to. We had to assume flatness, which means that this part of the boundary had to be essentially a plane. Okay, and he was able to do it for convex domains, much more general. So it's also very nice work. We did for nonlinear diffusion with Atushi, and for P Laplace, it's becoming a mess to compute the auxiliary function and so on. And okay, the proof is again a kind of Friedmann-MacLeod device. It's a 2D version of the Friedmann-MacLeod function, xy, and you have to combine this with all the information available, which is barriers, Bernstein type arguments, Serine-Corner lemma, and non-generacy. In fact, if you use this function, if you integrate in X, once you know that it has a sign, because you can prove a maximum principle for this function, once you know it, by integration, it means that you have a profile like this, in the y direction for any x positive or x non-zero, okay? And in fact, we can show that this is too degenerate to be a real blow-up point. So we have a like in gigacone, a kind of non-degeneracy lemma. And so if the profile is not degenerate enough, not let's say not non-Lipschitz enough, like this, it cannot be a blow-up point. So the conclusion is that for x non-zero, there are no blow-up points, so it's a single point gradient blow-up. This is the basic idea of the proof. I cannot go to details. Okay, now open problems. We would like to know that in 2D, blow-up set is finite, like in Chen-Matano for the Fujita equation in 1D, or maybe even better that the M-house of measure is n-2, like in Velasquez for Fujita. This is very, very different because we don't have energy. All these things are based either on, okay, zero number, this is Chen-Matano, this was 1D, but here now we are 2Ds, so we don't have zero number. And Velasquez heavily used the energy for the rational structure of the Fujita equation. We don't have a clear rational structure. Okay, special profile maybe it's too much, so maybe I'll go to continuation, or I don't. How many? Do I have 5 minutes, or is it already too late? How much time?
Okay, please continue. Yes.
Okay, so maybe I will skip the. Okay, special profile is also interesting because. Okay, this is special. Okay, maybe a few words. Special profile in the normal direction, essentially given by this number 1/(-1) in the normal direction. But much more interesting is what happens in the tangential direction. So there is a elliptic Liouville theorem which I would like to advertise. We proved it with Roberta Filippucci and Patrizia Pucci 2 years ago. It's a simple, very simple problem. It's one dimensionality for this problem. You are in a half space. It's the elliptic problem, and you want to show that a solution of this problem has to be one dimensional. So then you just solve the ODE. So it's a moving plane argument. The proof is not very difficult, but the consequences are very useful because with this kind of rigidity theorem, one dimensionality theorem, you can show that the profile in the tangential direction has to be more singular than in the normal direction. So the consequence is that, okay, if you look at the equation first, if you look at the equation, it says that the tangential derivatives are lower order, are less singular than the normal derivative. So the main behavior in the equation is u nu behaves like u nu to p. So this is the main mechanism to understand the profile. So okay, it's fine for the normal profile, but it gives absolutely no information on the tangential profile. This is a consequence of the Liouville theorem. So for Liouville profile, the only thing you can say is that it has to be more singular because since the derivatives are slower, it has to be more concentrated. Otherwise, you could not reconnect with the regular part of the profile. So okay, but it's very weak information. It's more singular. Now, if we want to compute the real tangential profile at near a single point boundary point, we have to make more assumptions. So let me skip this. Okay, yeah. So this is a general result. This one you can derive from the Liouville theorem is that it's more singular in the tangential direction. This is when you move along the boundary to the blow-up point at the final time. So essentially the tangential derivative is zero because it's zero on the boundary, but all the information is contained in the normal derivative, and so the normal derivative behaves like the power beta, which is 1/(p-1) in the normal direction, but in the tangential direction, when you move along the boundary, it has to blow up faster or to reconnect faster. The question is how much faster? And so we were able, with Alessio Porretta in an earlier paper, we were able to compute an exact tangential profile under additional assumptions. First of all, p between 2 and 3. I mentioned this kind of technical research before. Locally flat, this is just for convenience, and monotonicity in the tangential direction. In other words, you want to assume that the solution is decreasing away from the slice x equals 0. So this is the singular slice with the black line. Then the same picture as before, and you want to ask at what speed, how fast is the derivative regularized when you move away in the in the tangential direction. And so the answer is x to the minus 2 over p minus 2. So again, it is not self-similar. Now the full profile at the final time, so it's a capital T, is given by this. So it's like a kind of parabolic profile in the xy plane. And so it's y to the 1 over p minus 1 in the normal direction. Y is a normal coordinate. And in the tangential coordinate x, so it's this because at the end you get 2 over p minus 2. So it's very strange because it's completely another anisotropic. Pretty much different from the Fujita equation. So, okay, these are interesting questions. Now I have to skip all these. I'll just maybe say something about viscosity solutions. So viscosity solutions, you can take the standard definition of viscosity, otherwise you can do it by approximation and truncation. So you truncate the nonlinearity by something like this, grad v square time this truncated coefficient. So you have global smooth solution, and there are it's a monotone approximation. So solutions, the real solution will converge monotonically to the the sequence of solutions will converge monotonically to the real solution. And the real solution, what I call the real solution, is a generalized viscosity solution. So it's written here in the viscosity sense, but it's not very intuitive. And it says that you can lose boundary condition. If it has to, it can lose boundary conditions. And in that case, the equation will be satisfied up to the boundary in the viscosity sense. This is not very intuitive. So you can see like this approximation, and then so you have this monotone convergence to the viscosity solution, but not uniform up to the boundary. In fact, you can show that it is continuous up to the boundary, the viscosity solution, but not necessarily zero on the boundary. So it's very strange because it is zero in the viscosity sense, but it is positive in the pointwise sense, which is well defined because it is still continuous. So this is a typical viscosity loss of boundary condition. And it's much more intuitive when you see this as a boundary layer phenomenon when you try to approximate by monotone approximation the viscosity solution by regularized and truncated problems. It's the way I prefer to understand it. So, okay, so you have this loss of boundary condition. Does this really exist? The possibility was mentioned by Barl 20 years ago, but finally it was proved the real existence in the paper, but with Porretta and so no, it's a different thing, I would say. Okay, so does loss of boundary condition occur? In fact, the answer is yes and no. So yes, this exists. So there were independent results with Porretta and independently by Alex Quast and his student Rodriguez. And so the result is yes, for large enough initial data, you have loss of boundary condition, but also you can even have it lose boundary conditions everywhere after some time. But you have also exceptional solutions which blow up, gradient blow up, but without losing boundary conditions, and they are regularized immediately. They arise as minimal GBU solutions. For instance, you do a shooting, you shoot around a long array of initial data, and you take the minimal one for which singularities occurs, and this is typically a gradient blow up solution without loss of boundary condition. So it's exceptional. You can prove that it's really only one in each direction. Okay, these are okay. And another important result, which was proved before by Porretta and Zoisroy, is that for large time enough, solution becomes classical and C1 for forever, and it decays. So it means that there is an interval of time between first blow up and last regularization term where the solution can do weird things. And recently we have been trying to understand these weird things. So let me give you some pictures. It's another paper with Mizoguchi, and also we were previously we had results with Porretta in another paper. Consider the singular time. So singular, see, it's 1D because in 1D it's much more precise. So the singular time set means that these are times where solution is still zero on the boundary, but the derivative is already infinite. So these kind of transition times between losses and recoveries of boundary conditions. So first of all, with Mizoguchi, we showed that this set is finite, always finite. And on each interval between two consecutive times like this, the solution is either classical up to the boundary, or with loss of boundary condition. So we mean that, okay, typically you have this kind of behavior. You have classical, then loss, classical, loss with maybe changes of, okay. And also you have, so you cannot see it on this picture, but on your next picture, you have, okay, solutions with immediate recovery. So, okay, this is another example. Here you have, okay, classical, loss, classical, and here gradient blow up with immediate regularization. So, and nothing else can happen in 1D. So it's a complete classification again. So this is formalized in the theorem 2. So we prove that for any M, there exist solutions with exactly M times of loss of boundary condition and M time of regularization. But conversely, for any finite sequence of types, classical C or L, C for classical, L for loss, in any given order, you can find a solution which realizes this sequence. So you can find, for instance, you can produce, for instance, bouncing. Bouncing is also a possibility because if you have classical loss and then immediately recovery and then loss again, this is like bouncing, and multiple bouncing also possible. Actually, any sequence like this can be realized for some solution. So this is a classification which is based essentially on zero number theory adapted to viscosity framework through regularization, for instance, because we cannot, okay, the zero number theory is flexible enough after some work to cover such situations. Now in higher D, we don't know much. So probably I have to skip the next slides. Maybe, okay, maybe, okay, oh, this is too much. So, okay, higher dimension, we don't know anything, except that, okay, we have some regularization rates, for instance. We know that as a like kind of dual estimate to the gradient blow up estimate, we have regularization estimate like this, but the classification of the zoology between the two times in higher D is completely open. So I will stop here.